Hey, welcome back, chemistry students. I'm Mr. Silverstein. Today we're going to be moving into those magical elements known as transition metals. So get out your unit pack, your polyatomic ion sheet, as well as your periodic table. Turn to page 15 in your unit pack, take some personal notes, and we're going to find out about transition metals. I'm going to share my screen and let's get started. So this is part of our unit on bonding. We are naming ionic compounds, and this is transition metals, Unit 5, Concept 2, Part 5. And our objective is to understand transition metals on the periodic table of elements. There's going to be 2 practice assignments when this is done. You're going to need some scrap paper to make sure that you can work through some of these formulas, but it should be pretty easy. So if we recall from the periodic table of element, there are 18 groups. You have your metals on the far left. You have your noble gases all the way on the far right. And then we have these transition metals that we haven't worked with for a while. Things like tin and chromium and iron and zinc. And these are all considered the transition metals in this little lavender section in this table. And you might want to take your periodic table and just kind of block them out. So what are transition metals? Well, transition metals are unique in that they can have an incomplete inner subshell, allowing valence electrons in another shell other than the outer shell. Well, that's pretty complicated. But if we take a look at this illustration, we see that we have multiple energy levels, 1, 2, 3, 4 energy levels. In that first energy level, as you know, it can hold 2 electrons. In the second ring, it can hold 8. This third ring here can hold up to 10 on a transition metal. And then this outer one is holding upwards of 2, and this happens to be for titanium. Other elements only have valence electrons in their outer shell. And this allows transition metals to form different oxidation states or different ions. And so you can have tin 4 or tin 5. For example, titanium, that's this one that's here, is element number 22. It has 22 protons, it has 22 electrons, but titanium can form bonds using electrons from more than one of its shells or energy levels. That's pretty cool. So let's review periods again. On the periodic table, each row represents how many energy levels an element has. And each energy level can hold a limited number of electrons. So for example, level 1 can hold 2 electrons. Level 2 can hold 8. Level 3 can hold up to 18. Level 4 up to 32. And level 5 up to 50. And remember, for an element to be stable, it needs to have a valence electron shell that has 8 electrons, except of course for helium and hydrogen. They only need to have 2. Most elements have an even distribution of their electrons filling up each level, and the valence electron is the one that is not full or even. Transition metals have an uneven distribution of electrons, resulting in variable oxidation numbers or their charge. You might want to add this onto your notes. And of course, these slides are posted on your Google Classroom, so you can go back and review them. So what is a transition model oxidation number? Well, when looking at transition metals on the periodic table, you will not know the oxidation number until you have it bond with another element. And so we're going to need to see how many electrons the transition metal will give up and represent it in a formula with a Roman numeral in parentheses. And remember, metals form cations giving up electrons. And so we're really not going to know what the oxidation number is until we see how many electrons the other element's going to need to get. It might need 3, it might need 4. And then the transition metal can give that up because it can take some from one shell and some from another. Now the ion charges, transition metals have variable charges. And this table shows the most common charge. The charge is based on how they will bond to metals or polyatomic ions. And so if you take a look at your own periodic table, you can go in there and make some notations on some of these because these are the most common charges. So titanium can either give up 4 or give up 3. Fe, which is for iron, can give up 3 or can give up 2. Copper, which is Cu, can give up 2 or can give up 1. Lead, Pb, can give up 2 or can give up 4. Zinc, however, is always going to be zinc 2+, and silver is always Ag+. So silver can only give up 1. Transition metals transition because they can form many different ions. For example, sodium, which is not a transition metal, is always Na1 because it's in group 1, and group 1 metals have 1 valence electron, therefore they lose 1 electron to be stable. Iron, as a transition metal, can be Fe+2 or Fe+3, giving up 2 or 3 electrons. Because you can't determine the oxidation number from the periodic table, a Roman numeral is used to show it based on what is needed to form the bond. Let me repeat that. Because you can't determine the oxidation number from the periodic table, we insert a Roman numeral to show it based on what is needed to form the bond. And it'll be shown such as this: copper, parentheses, Roman numeral 1, or copper, parentheses, Roman numeral 2, meaning copper, or Cu1, is giving up 1 electron, or copper 2 is giving up 2 electrons to make that bond. And they would be represented like this: Cu+1 or Cu+2. Or it would just be Cu with the plus, making the number 1 just a common number. There are some exceptions, of course, for making these transition metals. So we want to write the name of the first element, the metal. And the exception is if it's a transition metal, include the Roman numeral to indicate the charge of the metal. Write the name of the second element, the nonmetal, with an IDE ending. So for example, I have copper and chlorine, CuCl. I can also have CuCl2. So CuCl would be copper 1 chloride, because it only needed 1 electron. And here, chlorine needed 2, so it would be copper 2 chloride. Now, how do we determine the Roman numeral for the transition metals? Well, we can use a reverse crisscross, that's an option. Or we can use visuals or math to determine what charge of the cation must be for the overall charge to be 0. Regardless of the option you prefer, always double check it. So let's take a look at this one. This is with a polyatomic ion. This is going to be SN3 with a phosphate. So we know The phosphate is PO4 minus 3. That's from your polyatomic ion sheet. We're going to crisscross this 3 over to the SN3, 4, and then we end up having tin 4 phosphate. 3 moved over here, but we're going to need the 4 for the tin, and it's represented tin IV phosphate. Another option, here's the same formula again. We can build them along the way. I know I have 4 phosphates, so let's cross this over and add them up. And we have tin 4 phosphate. Another option, let's take a look at example number 2, FeSO4. Since the 2 isn't there, it must have reduced. These are a little bit harder. What would it be? Iron 2 sulfate. We got our sulfate, remember it was a little bit minus 2. Iron, we're going to need that negative 2 from the sulfate, move that over to under the Fe. We're not going to use a subscript for the Fe. It's just going to be iron 2 sulfate. You can also build it out. And you see you need iron 2 sulfate. Let's watch Tyler walk us through transition metals. This is also added to your Google Classroom. Let's watch this together.
Let's talk about transition metals in ionic formulas. So the transition metals are the elements in this part of the periodic table. And when we write formulas for ionic compounds that contain transition metals, the formulas look like this, with these Roman numerals here in the middle. So this might be a little bit different from other types of chemical formulas you've seen. So in this video, we'll talk about what's going on here. Okay, so transition metals. As I said before, the transition metals are the elements in this area here of the periodic table. I've written some of the most common ones in. Now, I'm also going to be talking about some of the metals over here. Okay, these guys here aren't technically transition metals, but they act a lot like the transition metals in certain ways. So I'm going to be including them in the discussion as well. Now, for ionic bonding and ionic formulas, transition metals are a little bit different from the elements here and here on the periodic table. This is the reason why. Transition metal elements, or at least I should say many of the transition metal elements, are able to make more than one type of ion. And each one of these types of ions has a different charge. Let me show you what I mean. Let's start by taking an example that's not a transition metal. We'll take lithium in this column. Okay, so lithium. When lithium forms an ion, we know that that ion is going to have a +1 charge. And that's because lithium is in this column. Every single ion that lithium makes is always going to be +1. We know that based on its location. Now, the same is true for calcium. Okay, calcium is in this column here. So when calcium makes an ion, that ion will be Ca2+, and it will always, calcium will always make ions that are 2+. Every single calcium ion, for the most part, will be Ca2+. Now, on the other hand, transition metals are a little bit more loosey-goosey. Okay? Iron, Fe, for example. Iron can make an ion that's 2+, but it can also make an ion that has a 3+ charge. So it's able to make both these types of ions. Gold, which is another transition metal right here, can make Au1 plus with a 1 plus charge, or it can make a type of ion that's Au3 plus. Manganese, which is right here, is one of the craziest of the transition metals because of the huge variety of ions that it can make, okay? A manganese element can turn into Mn2 plus, or Mn3 plus, or Mn4 plus, or Mn6 plus, or Mn7 plus. So the point is, the transition metals can make multiple types of ions, and these ions all have different charges. This is different from the metals over here and from other types of elements on the periodic table, which tend to always make the same type of element based on what column they're in. Now, sometimes people ask, why is it that the transition metals are able to make this wide variety of ions? And the answer is kind of complicated, but basically, it has to do with the way electrons are arranged in the orbitals of the transition metals. Essentially, the transition metals are more loosey-goosey with the electrons that they give away. They're not set on giving just one away or two away. They can give a couple away, they can give a couple more away, and so that's how you end up with these ions that have varying numbers, varying amounts of positive charge. So, when we have these elements that can make different types of ions, how do we tell them apart? Well, we have to use a naming system that uses Roman numerals. I'll show you what I mean. So using this Roman numeral notation, we call the Fe2 plus ion, we call that iron 2, with a 2 in Roman numerals in parentheses. Iron 3 plus is iron 3. Gold 1 plus is gold 1. And manganese, for example, 4 plus, 6 plus, 7 plus, are written as manganese 4, manganese 6, and manganese 7. Now, you might be a little bit unfamiliar with how to write numbers in Roman numerals, so it probably wouldn't hurt to do a real quick review of Roman numerals before we move on. So here's how to write the numbers 1 through 10 in Roman numerals, okay? 1, 2, 3 are pretty straightforward. Then 5 is a V, and 4 is an IV because it's 5 minus 1. If a number is to the left, it's subtracted. So 1, 2, 3, 5 minus 1 is 4, and 5. Then we have 6, VI, 7, VII, 8, V with 3 I's, and then we have the same thing with 9. 10 is an X, and 9 is an X minus 1. Now, it's very unlikely that you would run into an ion that had a charge of 8, 9, or 10, but hey, this might just be useful to keep in mind anyway. Nonetheless, 4, 5, and 6 tend to be quite common ionic charges, so you want to be sure to know how to write these numbers in Roman numerals. So we're going to use this Roman numeral notation whenever we write formulas with transition metals, because we have to explicitly say what charge the metal has, because we can't just figure it out based on where it is on the periodic table. So we have to say manganese 2 chloride for a compound that contains Mn2 plus. For iron 3 oxide, we write that so that whoever's reading it knows that we're talking about a compound that contains iron with a 3 plus charge, okay? This Roman numeral notation is different from formulas without transition metals, where we just write calcium fluoride, where we'd write sodium sulfide. We don't have to use Roman numerals when we write formulas without transition metals because it's totally clear what these charges are, right? Calcium is in this column here, so we know for sure that it's 2 plus, and it's always going to be 2 plus. Sodium is in this column here, so that we know that it's 1 plus, and it's always going to be 1 plus. So we don't have to use Roman numerals when we write formulas without transition metals. And in fact, it would be wrong to use Roman numerals when you're doing this. So don't put Roman numerals into the formulas unless they have transition metals. So that's an introduction to transition metals in ionic compounds. We saw how one transition metal element can make multiple ions with different charges. In the next 2 videos, we're going to learn how to take the name of a transition metal compound and write a formula for it. And then take a formula and name it. Writing formulas is...
All right. So Tyler's helped us out understanding transition metals with ionic formulas. Let me go to the next slide here.
Let's talk about...
All right, it's practice time. I'd like you to pause the video and write the name of the compounds based on the formulas below. Remember, use your periodic table, identify whether it's a metal or a transition metal, and then write the formula. Let's do this together. I'll do the first one with you, and then you will practice on the next four. So we have FeCl3. Fe is iron. Cl is going to be chlorine. We know we've got 3 chlorines. How are we going to write this? This will be iron 3 chloride. You do the next 2, 3, 4, and 5, and then we'll double check them together. I'm a little late making my video. All right, let's see what you have. We have CrO, and that's chromium oxide. Mn2O7, we know we have 7 oxygen, so it's going to be manganese 7 oxide. Crn, that looks like it's chromium and nitrogen. So this would be chromium 3 nitride because nitrogen needed 3 electrons. Ag2S, that was going to be silver 1 sulfide because sulfur only needed 1. All right, let's summarize this. The transition metals are unique in that they can have incomplete inner subshell, allowing valence electrons in a shell other than the outer shell. Because you can't determine the oxidation number from the periodic table, a Roman numeral is used to show what is based on needed to form the bond. Use the crisscross method to determine how many of the element are needed and resulting the charge. Now, open up your next assignment tab. Do the practice on transition metals, L2. You're going to need your periodic table and your polyatomic ion sheet. I strongly suggest that you write them out on scrap paper first before you answer the questions on the quizzes. Then, after you've completed L2, go on to the next tab and open up assignment L3, transition metals with ionic compounds. Well, I'm Mr. Silverstein. That's all I have for you now. If you have any questions, email me or message me, and we'll get back to you shortly. You guys have a great day.